Welcome back to the part two of the lecture on natural language processing of the course Big Ideas in Artificial Intelligence. Now we have learned about the importance of language in understanding and studying artificial or any kind of intelligence in the first part. Now let's try to delve into how to build intelligent system that is able to understand or use language. In order to do that, we need to first talk about the one major purpose of language, that is for us to perceive the surrounding environment. Just like vision that we have learned from previous lectures, language is our way to perceive the surrounding environment. By hearing or reading what others have said or written down, we know what they perceive of their surrounding environments. Thereby, we know more about the world in which we are. And also by listening to the expressions made by others, we know what they think and how they feel. And of course, those other people or other intelligent agents in our surrounding environment are parts of the world in which we are. And thereby, as an intelligent being, we want to perceive the state of. However, language is unlike vision or other sensory modalities via which we observe the surrounding environment. Language, the language that we use, is the result of our intellectual capability. It's not the result of the universe or anything that is given to us by the universe. In other words, language is artificial and is in fact not at all natural, although the title of this whole lecture is called Natural Language Processing. This artificial nature of language implies that there is no inherent nor natural concept of similarity. Let's just consider one simple example. 3 words in English: quiet, quit, quiet. If you look at the spellings of these 3 words, you notice that they are extremely similar. Quit is spelled as Q-U-I-T. Quiet is spelled as Q-U-I-T, the very same thing, plus the extra E at the end. Quiet, on the other hand, is spelled as Q-U-I, extra E there, and T. However, if you think about the meanings of these 3 words, they are very, very different, unlike how they are spelled. And the lack of natural metric of similarity is even severe if we consider the fact that there are more than 7,000 living languages in the world. And interestingly, among all these thousands of living languages, we can almost always go back and forth between any pair of languages. What that means is that most of these languages are complete. However, when you look at how these languages express different meanings in sentences, words, or whatnot, we notice that these languages seldom share any common forms. So taking the exactly same example of 3 words, quit, quite, quiet from the previous slide, and then let's look at their translations in Korean. Quit can be translated into 관두다. Quiet can be translated into 거의. Quiet can be translated into 조용한. And you do see how arbitrary this choice of words, letters, writing systems, and even pronunciation are. However, those 3 pairs are exactly the same thing, just written in 2 different languages. What really that means is that there must be some kind of similarities or the metric of similarity underlying natural language or the human language. However, it is not apparent or easy to capture at all. Now, what can we do? It turned out that there is a very interesting concept or the hypothesis that we can rely on that is called a distributional hypothesis. And then this hypothesis can be succinctly described as this phrase: a word is characterized by the company it keeps. That is, the meaning of the word, let's consider a word, but it doesn't have to be. The meaning of the word is not in the word itself, but the context in which it appears. Of course, this context should be interpreted broadly. For instance, you can think about textual context, which tells us about the text or a sequence of words in which this particular target word of which the meaning we are interested in appears. Of course, another case would be multimodal context. So we have a word or a phrase that we want to know the meaning of, and then we can look at what kind of other modalities such as vision images or speech or whatnot appear together with. As you can see on the slide, there's an example. So I took this from the Twitter account called the Book of Rather Strange Animals. And then there we have a picture of a snake, in particular the elephant trunk snake, and the caption that says the elephant trunk snake. And by looking at this image that accompanies the elephant trunk snake, I get the meaning of the elephant trunk snake. That is that it is a snake that I see. Now, of course, in this lecture, we're going to almost entirely focus on textual context only. Now then, in the case of the textual context, what we now want to know is so-called textual co-occurrences or the word co-occurrences. And then we are very much sticking to the first idea of distribution hypothesis that can be described by a word is characterized by the company it keeps. Let's just take as an example of NYU. Now we want to know the meaning of this word NYU. Let's say we go to Wikipedia and search for NYU, and then what Wikipedia is going to give us is a list of sentences or the snippets from the Wikipedia articles that contains the term NYU. Some of those sentences include, for instance, NYU also has the 2 overseas degree granting campuses, NYU Abu Dhabi and NYU Shanghai, and has distant academic centers. Another example, New York University Shanghai, the Portal campus is part of NYU's Global Network University. Let's look at yet another example. New York University School of Law, sometimes shortened to NYU Law, is the law school of New York University. New York University, NYU, is one of the world's premier residential research and teaching institutions. And then examples go on and on. But then, do you see what I see? By simply looking at all these sentences in which NYU appears, I almost feel like I get this sense that I know the meaning of what NYU is. And how do I know that? Or how did I get the sense? Is because I see a patterns of the words that appear together with NYU. I see that the center, word center, appears together with NYU. For instance, in academic centers or the academic medical center. Or I also do see that the New York University, this phrase really appears frequently together with NYU. And for instance, NYU Violets is the nickname of the sports team and the other competitive teams at New York University. And I also see that the school, the word school appears together, such as in business school and law school. So what that means is that the context in which a word appears, or could be a phrase, doesn't really matter, as you can kind of guess from now, gives rise to the meaning of the word itself. And then NYU in this particular example seems to mean, according to our search in Wikipedia, New York University, probably university. NYU seems to refer to some kind of center. NYU seems to refer to some kind of school, because these phrases or words appear together with NYU, that is co-occurred with NYU. So then now we can think about building a table or matrix of co-occurrences. We're going to consider the meaning of the word, individual words. So for each word, we're going to go through a large amount of data sets, such as entire Wikipedia, and then trying to see for every possible other word or phrase whether this target word and one of those phrases co-occurred or not. And then we're going to count the number of those co-occurrences. For instance, in our example earlier, NYU and the phrase New York University occurred 5 times. So we're going to count this co-occurrence as 5. NYU and phrase New York appear 7 times together. And then we can do that for as large data set as possible with the latest and greatest compute architectures or the compute resources. And what we end up with is so-called word co-occurrence matrix, where each row corresponds to each word, and then each column corresponds to a co-occurring phrase or word. And then each entry in this matrix corresponds to the number of times the corresponding word and the phrase co-occurred in a large database of text that we have collected. And then it's becoming increasingly easier to collect such a data set thanks to the availability of large amount of the public text on the internet. Now, once we have this word co-occurrence matrix, we suddenly have a concept called a word vector. And then this word vector corresponds to a row in the word co-occurrence matrix. And what we realize based on the distributional hypothesis is that any 2 words with similar word vectors have similar meanings because they appear in similar context. And as Firth in 1957 elegantly put it out, we know the meanings of those words by looking at their company, that is, the phrases and words that co-occur together with them. If they are similar, then the meanings of these 2 words must be similar as well. Another way to think about it is that the similarity between 2 words, or the similarity between the meanings of the 2 words, is directly reflective of whether we can replace one word with the other. If the context in which they appear are very, very similar, then of course that just implies that we can replace them. And any 2 words that can be replaced are indeed similar in their meanings. Now, unfortunate thing about this word co-occurrence matrix is that these word vectors are very, very sparse, meaning that there are a lot of zeros, while it is very high dimensional, because we need to consider all possible co-occurring phrases. And a lot of zeros make it really difficult to compare these two or pair of word vectors because their similarity, which is often computed using so-called dot product, will almost always be close to 0, regardless of whether a pair of words are actually similar or not. So what we want to do, it turned out, is to compress this very large but sparse, that is, it has a lot of zeros, this very large, very sparse word co-occurrence matrix into a much smaller, in fact, a smaller pair of matrices. So we start with the original co-occurrence matrix that has n rows that correspond to n words, and then m co-occurring phrases, and both of them are very, very large. And then in this large matrix, we have n times m many counts, although most of them are 0. Now what we're going to do is we're going to compress them into 2 matrices. The first matrix contains n many rows that correspond to n many words, and then each row has only d many numbers that are not necessarily count. The second matrix has m many rows, where the m corresponds to the number of co-occurring phrases in the co-occurrence matrix, and then each row has again d many numbers, where d is much, much smaller than either n or m. And then by multiplying the first matrix with the transpose, that is the 90-degree, let's say, rotated second matrix, we try to make sure that the product of these two matrices is going to be as similar as possible to the original co-occurrence matrix. So it is a compression, but we are going to let information be lost to a certain degree. And then for each count, that is the count of a pair of words and a co-occurring phrase can be reconstructed by computing the dot product again we talked about in the previous slides between the word vector and the co-occurrence vector, both of which are d-dimensional. Now, it turned out that how this matrix factorization technique compresses the word co-occurrence matrix is by putting similar words and similar co-occurring phrases nearby in this much more compact d-dimensional real value space. And then this is how the whole idea of the matrix factorization compresses this very large sparse co-occurrence matrix. In other words, compression is how we automatically capture the similarities among different words. Of course, it turned out that the compression can be a bit tricky because that implies that we need to build the co-occurrence matrix offline, and this co-occurrence matrix can be gigantic and very inconvenient to maintain and manipulate. It turned out that the brilliant idea is to view the compression as prediction. So in earlier lectures in this course, we have learned about what it means to predict some kind of output or category given the input. We can use the very same idea in order to replace the whole idea of compression or the compression of all these counts into vectors with predicting the counts given these vectors. That is, what we want to do is to make sure that this word vector and the phrase vector, when we computed the dot product of them, is going to be as similar as possible or is predictive of the count or the co-occurrence count of that particular word and the particular co-occurring phrase. And this technique is often referred to as word-to-vec because we're turning a word into a vector by predicting or making sure that this vector is predictive of the count that is the co-occurrence count, and was proposed in 2013 and has been improved over the many years. And then nowadays, this is de facto standard for us to induce this continuous vector representation of words. One of the amazing things that sparked this whole interest in using deep learning, or more broadly, artificial intelligence for natural language processing, was the fact or the observation that these word vectors that are induced by word-to-vec technique that we have just talked about were compositional. And then this compositionality can be exploited or observed simply by performing vector arithmetics in this space of word vectors. So what do I mean by word vector arithmetics is that we're simply going to take multiple words and then either sum or subtract some of those vectors and then see what the resulting vector looks like by finding the word whose word vector is closest to this resulting vector. So for instance, if I start from Russia, and then I'm going to subtract China, and then add Beijing, the nearest vector is going to be of Moscow. Hold on. I'm sorry, this is my mistake. If what should have done is that if I subtract Moscow from Russia, and then add in the Beijing, then that is going to be very much similar to China, which actually is the correct thing according to the site. I'm sorry, this is quite confusing always, but let's take the second example. So we start from Portugal, whose capital is Lisbon. What I want to do is subtract Lisbon. So that is, I'm going to subtract the capital of this Portugal and then add in the Madrid instead. Now, all these things happen in this d-dimensional vector space, and then I'm going to look for the nearest word to this resulting vector. That is Portugal minus Lisbon plus Madrid. And it turned out that the nearest vector is Spain. And then these are not even cherry-picked examples. These observations can be made for almost arbitrary choice that you make, as long as that choice reflects the real world or according to the data you have. And this was one of the strongest evidence that word vectors are compositional and also do indeed capture the meanings of the words. And thereby we can use these word vectors in order to make an artificial intelligence systems that can understand human language as well as we could. And that's it for the second part. We are going to look into what happens if you want to look at the meanings or trying to capture the meanings of not a single word, but the entire sentence or the entire text where it's not only a single word, but the context itself is very important. And then that's going to allow us to think about the meaning not only of the individual units, but of the actual language. And we are going to talk about that in the third part. Bye-bye.